Hello everyone and welcome to another episode of Solving Advent of Code in Rust and Try to Learn Rust in Between. I'm Roberto and we have this way.
Luciano, hello.
If you never did Advent of Code is a code challenge that is published every year around the Christmas period. We are working toward the last year one. There are 24 challenges and you can find them on adventofcode.com. We are publishing all our code here, GitHub. And we have a YouTube channel where we publish all the recording. You can find the link in the description of the Twitch channel. We left in the last episode at part 1 of exercise 8, and now we have to do part 2.
Yep, and because this one was particularly complicated, I suggest we reread all the README and we briefly review part 1, which should be very quick. But basically, the idea is that we have a display that shows digits, and there are 4 digits, and of course, they can be from 0 to 9, and they look something like this. Imagine these are all the possible digits you can get. Every digit is made of segments, and there are 7 segments. And depending on which segments are turned on, you get different numbers. For instance, here the segment A, B, C, E, G, and F are turned on. This one in the middle is turned off, and this is the number 0. Then you can have the number 1 if you turned on the segment C and F. Number 2, you turn on this one, C, D, E, and G, and so on. So basically, you just need to look at the segments that are active to detect which number is being displayed in one of the positions of the display. Now, the problem is that the signals that we are getting are broken because this display is kind of broken and all the signals are kind of shuffled. So we'll need to understand just by looking at a sequence of segments that are active at a certain point in time, we should try to infer which numbers should be displayed. Now, I'm probably explaining this very bad, so let's see an example. So our input looks something like this. This will actually be all in one line, so keep in mind that there is a split here, and these are 2 different parts, this first part and the second part. Now, the first part, what does it mean? So this first part is basically signal patterns, and it's basically 10 different ways the submarine tries to render a digit using the current wire segment connections. So we are in a submarine, there is this display, the wires are kind of shuffled, we are observing signals, and we are displaying.
So left of the pipe, there will always be 10 configurations because we have always 10 figures. On the right, it can be a different number based on whatever.
Exactly, yeah.
And from a line to another line, the shuffling of the wires can be different.
Yes, our input actually looks like this. And we need to look at lines independently because every line has a totally different configuration and will produce a different number because of that configuration. So it's like these wires are constantly changing configuration. You can look at that this way. So let's see a better example. Now here, I think we'll need to look at this on GitHub. So let me go to GitHub.
Because our README is formatted in a fancy way, and we
exactly.
can't read it. We can't read it.
So let me put this one here on screen, make it a little bit bigger. Now here it should be easier to visualize. So for the first part, what we want to do, we just want to look at the second part. And actually, one thing that I didn't mention is that if you look at these numbers, only by counting the number of segments that are active, certain numbers can be guessed immediately because there is only one possibility.
Yeah, for example, one has always 2 segments on and nothing else.
Exactly, and there is
4
no
has
other number that has only 2 segments active.
4 is the only one with 4 segments.
Exactly.
7 is the only one with 3 segments. And 8 is the only one with 7, with all of them.
With all the segments, exactly.
With all 7 of them. Instead, 6 and 9 can be switched because both of them have 6 segments, and so on. 2 with 5 and 3, and 0, 9, and 6 are in another subset.
Exactly. So the first part of the problem is a little bit simpler because what we need to look for is only try to count the numbers that can be guessed immediately. I think that was the assignment. Let's double check. Yeah, so they call it the easy digits. And basically, we need to focus only on the easy digits. And the question is, how many times the digits 1, 4, 7, and 8 appear? And this is actually very simple to solve because we just need to look at the second part of every line and count only the strings of a certain length in these 4 strings that we get for every line. For instance, you can see this one is in bold, 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 because this represents the easy digits just because of that length.
Yeah.
So this is a quite simple problem to solve, and let's review very quickly the solution that we already discussed last time. So if we go to part 1, what we do is we get the input, we split by lines. Then for every single line, we do a map, and that map basically splits the line in 2 parts, looking at this space, pipe, space. At this point, we have a tuple made of 2 parts. We ignore the first part because we only care about the second part. And this is what we call the raw output values. And now here we are doing another map where for the right side of the line, again, we split by white space and we filter only for the ones that match those lengths. So either 2, 3, 4, or 7. By the way, compared to last time, I did a small change because here we were actually using before an hash set and doing in that hash set. Here we just use a matches, so we don't even need to allocate an hash set. It's like,
is it faster?
I tested it and it was like 15 times faster or something like that.
Okay, yes, it's
because
faster.
It's like if statements. So rather than checking in a hash set every single time.
And here the pipe, what meaning does it have? I mean, is an OR, okay. But it's not a bitwise OR.
No. This is literally a match statement checking that this length, so this is going to return true or false based if this value matches this pattern. So this pattern is literally value is 2 or 3 or 4 or 7.
On the right, we have a pattern. Okay.
Exactly. So this is kind of a shortcut for a match expression.
Question. If you write in a normal Rust line 2 pipe 3, pipe 4, pipe 7, and you assign it to a variable, what is that? Is a bitwise OR?
In that case, I think it's a bitwise OR. Here, this is not an expression, but it's a pattern.
Here it changed meaning because of the matches macro.
So that pretty much is, let's rewrite it very quickly. That's pretty much like filter. We have S, and then what we are doing is match on s.len, and then the cases are, it will be something like 2, we return true. Then we have 3, we return true.
Okay.
Sorry, it was 3, 4, and 7. Yeah. True, and 7, we return true. And then everything else, we return false. So this is pretty much the same thing, except that once you have all of these that are the same, you can simply write it as 3.
Okay, cool. Thank you.
4, and 7. And if you do this, actually, Clippy should complain because it should realize that you are doing a match expression that returns true or false. So it's easier to just write the matches as macro. So rather than writing a proper match, you just use this macro, which is kind of a shortcut.
Cool. Now it's clear. Thank you.
Okay. So what we do here, we're basically saying split by white space, keep only the pieces so that the words in this string that have either one of these lengths, and then count all of them. And then at the end, for every single line, you sum everything together.
Nice.
And that's it.
Part
And
2, I think, is more complicated. Let's
if
look at
we
the
run the
readme.
test, just to be sure,
Okay. Yeah.
that should
Sure
work.
that we didn't break anything. Okay, still working. Cool.
Perfect. Let's look at part 2 at this point. Let's go again in GitHub because that should be more readable. So here is where we need to use deduction, because here we actually want to know every single number, not just the easy digits, but we want to be able to guess, well, not to guess, to infer what are the every single digits. So what's interesting here is that so the mapping between signal wires and segments only makes sense in the following configuration. So this is a particular example, right? And basically what they are figuring out here is that this is A, this is B, this is C. Based on these readings, they figure out what are the segments. And with that, then you can deduct the numbers. So if you see A, C, E, D, G, F, B, that is an 8 because these are all of them. Then if you see C, D, F, B, E, this is a 5, and this is because you have C, D. Yeah, so it's basically a 5 because you have these segments here. This, and this. And so on. So we basically need to be able to write an algorithm that, given this input, is able to figure out which letter is positioned where. And then once we have that configuration, we can decode the actual four numbers there. Yeah, the actual 4 digits, which will make up a number.
And for every line, we have to sum everything together.
And then we need to read those as integers. And then I think we need to sum everything together. Let's verify that. So for each entry, determine all of the wire segments connection, decode the 4-digit output values. What do you get if you add up all the output values? So in these examples, we get 4 digits, a number, a number, a number, a number. You sum all of them together, and that will be the solution. Now
our input is longer.
Yeah, our input is much longer, and we get more readings. On the left side, we get 10 readings. On the right side, we always get 4 numbers. Now, one thing that I remember is that this one can be solved in a similar way to other exercises that we did last year, which is you basically have a number of possibilities, and you have a set where you have different items, every one with different possibilities. And there is always one item that is certain, or at least one. So you use that certainty to start to remove possibilities from the other set. And by doing that iteratively, if that's an English word,
in a loop,
you basically are able to infer all the possibilities, because eventually you will have something with 2 possibilities. You are able to remove one of those 2 possibilities, and you have a new certainty. Then you use that certainty to remove other possibilities from the other sets, and eventually you are able to map things one-to-one. And here, the interesting deduction I remember was that if you look at certain numbers, let's go back here. For instance, if you know, you will start from, for instance, 1, right? Because 1 is one of the easy digits or sure digits. And if you are able to tell that 1 is made by C and F. So if you're able to map two different items, then you know that C will also be present in 2, in 3, in 4, in 7, in 8, and in 9. So you can use this information to start to make more inference there. Does that make sense, or am I explaining it very badly? We also have a little bit of a background music.
Sorry. The ice cream truck on the street. Yeah, basically what you said. You have some configuration. For example, if you have 6 segments, it can be only a 0, 9, or a 6. But the 0 will be the only one that doesn't have a line in the center.
Exactly. Yeah.
So starting from the no numbers that are 1, 4, 7, and 8, you can know that the line in the middle is present in not 1, not 7, in 8, and in 4, but not in 7 and not in 1. And then you say that line can't be in 0. At that point, you know what 0 is. When you know what 0 is, then you can infer the 9 probably, because the 9 will be the only one.
It will have one more segment and one less segment, basically.
This also is true for the 6, but the 1 and the 9 will be overlapping. Instead, the 1 and the 6 will not. So
exactly,
9 is containing 1, and 9 is containing 4, and 9 is containing 7. So 9 is the only one that contains all the one that we already know, and so on. With
the interesting thing to keep in mind is that we don't really know the position of the segments. We only know in a set which segments are active.
Yeah, we work with sets.
But that's enough for us. We can make set difference to figure out what overlaps. Okay, should we look at the solution? Is that clear enough what we need to do?
Yeah, I think it is.
Okay, let's go to the code. Right, so let's see what did we do here. So here we need to do a slightly different parsing, because of course now we are interested in reading both parts of every line. So now we have row readings, which is the left side of the line, and then row output values. By the way, this is a function that is just parsing one line. Then we'll be reusing, let's actually look at this, because I mean, it's an easier starting point. Given that we have a function that does all the hard work for one line, what we are doing here is literally splitting by lines, mapping every line to that function. That function is just going to give us the number decoded for that line, and then we just do a sum. So this is super simple. What we are doing here is just looking at the problem from the perspective of solving one line at a time and just getting the output number. So with that in mind, here we will have a line. We split the line in two parts based on the separator. Then the readings, what we do is basically we split by white space. Then we do a map that is basically collecting all the characters in a set. This is using a B3. It could be an hash set. Doesn't really change much.
There is a reason behind using a B3 instead of an hash set?
I think I did some performance testing. We should do that again. I have a feeling that it was slightly faster, and probably because with small values.
Yeah.
Because here we have just a few chars in the set of possible values. And also the number of items is always very low because the maximum is 7, right? So a B3 will be much faster because you are not doing all the hashes. Basically, you just follow the tree. You just do comparisons, which should be faster than doing hashes for small items, I guess.
Okay.
But we should double check if this is really true with the latest version of Rust and how fast that is, if it is fast.
We have benchmarks, yes.
So basically, just review very quickly the input. That basically means that for every word on the left side, we create an hash set, and that hash set contains every single character that we find there. And every character represents a segment that is active in that particular reading. Make sense?
Yes, because we don't care the sort order of them.
Exactly. We're just saying this particular segment is on in that particular reading. Now we do something pretty much similar for the other side. We could have probably wrote a function and then just...
It's exactly the same, I think.
Yeah, it's exactly the same. So we could have written a function and reused that function in both.
Yeah, but
values.
This is still the parsing, so let's go.
Then what we do is readings by parts, which is basically... so what are we trying to do here? We are doing an array that contains 8 vectors of sets. Let me try to remember what we're trying to do here.
Because every digit can be a combination of sets, so we start putting everything in there and removing from the vector while we go through. At one point, the vector will be length 1, and then we have the mapping between figure and the right set that is representing that figure. Probably.
Yeah, exactly. And there are 8. Why? Because 8 are the number of segments.
The number of segments is 7.
It's 7. So why did we do 8 here?
Because there can... good question, because there can be a maximum 7 segment in... because it's 1 to 7, you don't use 0.
Oh, right.
Because you use the length of the reading as an index. So you use 1 to 7 as an index. You are never using 0.
Just to keep it simple, so that
to avoid it to be always -1 in everywhere, and that is bothersome. I mean.
So basically, in this array, we will have, just looking from number 1 to number 7 indices. From number 1 to number 8, we will have all the possibilities trying to figure out which segment is that.
Yeah, 1 to 7 included, or 1 to 8 excluded 8, because you were never indexing 8. Because there is no numbers with 8 segment.
Okay, then we start to populate this thing, and we basically say for every reading in reading, so we will have reading is basically this thing. So this will be an iterator of B3 set. So for every set, basically there.
For every set, we take the length and we put it in an index that is the same as the length. Obviously, for 1, 3, 4, and 7, there will be only one element in that stuff.
Exactly, yeah.
And is what you are doing between line 32 and 38.
Yes. Now, why did I do also this mapping thing? Because this is the opposite exercise. So here I'm trying to say, I know which set represents which digit.
Number.
And basically here there are certainties, and I'm already filling the mappings for those certainties. So I'm saying, okay, I already know that the one that has length 2 is number 1. The one that has length 3, meaning 3 segments, 7. Is number 7. 4 segments is number 4. 7 parts is number 8. So all these mappings are our starting points, our certain assumptions. Then at this point, we know...
Number 9.
Yeah, now here I was doing a bunch of deductions. So I know, for instance, that the number 9 contains 6 parts and contains the parts in number 4. Does that
Yeah.
make sense?
Yes.
So if you
because like
picture the number
before,
9, right? You have 6 parts, but if you take number 4, it perfectly overlaps all the segments in number 9.
yeah, with 6 parts we have 3 options: 0, 6, and 9. But 9 is the only one that is over 4 is overlapping with 4. So 4 is overlapping with 9. But yeah, they are the only. Is the only number that has some all the segments in common.
And this is useful because we already know exactly all the segments that are in number 4. So we need to basically find that item that contains all the segments of number 4 and has a total number of segments of 6. And at that point, we know with certainty which segments constitute number 4, number
Which set,
9.
which segment that is a set of letters constitute the number 9, and you are removing it from the set, from the vector, sorry.
Mm-hmm. So this is literally what we are doing here. We are iterating over all the possibilities. We are getting the position. So this one is like a find that gives you the index.
Okay, dot position is new to me, and is a find that gives you the index of what you find.
In JavaScript will be the equivalent of index of.
Index of.
Yeah,
okay.
Pretty much. And of course, it gives you an option because it might not find the object. So yeah.
Instead of giving you -1, is giving you an option.
A better result.
Yeah, a more semantic result.
And the other cool function is superset, which basically allows you to take one set, pass another set, and it will tell you if the starting set, so if S contains this one.
But well, here is the other way around. It tells you if mapping of 4 is contained in S.
Here is telling you if
mapping 4 is contained in S, not if S is contained in 4. If mapping of 4 is contained in S.
Yes, so S is a superset of.
Yes, S is the superset. Okay, cool.
And we unwrap because we know that the input is sane and that this number will be there. So at that point, we find the position, and based on that position, we say mappings 9 is going to be that position that we remove.
And we remove it from the vector.
And we remove it from readings by part 6.
That is is a vector, yeah. It's a vector.
This one is a vector.
Reading by parts is an array of vectors, so that will be a vector.
Yes. So basically, this means all the possibilities.
We don't have to unwrap here. I mean, if you remove out of bound, it's just panicking like crazy.
Good question. What does remove do?
Yeah, because if you remove 22,
panics. Look at this. Panics if index is out of bounds.
Perfect. So here we don't have to unwrap, because if we are out of bound, it's just okay. We can't be because we checked with position. Mm-hmm. But if it happens for any bug that we do, it's just panic.
Exactly. Cool. Yeah. It's probably one of the few functions that panics rather than giving you
an option
or a result. Okay, so basically this is the logic that we'll need to apply in a way. Basically, if we do it in the right order, if we find the right overlaps, we find more certainties and remove uncertainties to the point that we
9 and we don't have to deal with that 9 anymore. Now we have a 0 that is made of 6 parts again and contains a 7, while 6 is made of 6 parts but doesn't contain a 7 because it's lacking one segment on the top right.
Mm-hmm. And also remember that every time we do this, we are removing an option here. So now the things with 6 parts will have one less option. So here we do the same logic and we keep going. Then at this point, we know the number 0.
We only have one stuff in reading parts of 6, and that's 0.
And that's the remaining one, which is the number 6. So just to recap what we just said, if we just look at all the things that have 6 segments, 6 parts, we know that there are three possibilities: the number 9, the number 0, and the number 6. We get the number 9 by just looking at that only option of the three options where number 4 perfectly overlaps. We remove that particular instance. Then we can guess number 0 by looking at what overlaps number 7, which is another certainty that we had at the beginning. At that point, we have only one option left with 6 parts, and that's going to be by exclusion number 6. And basically, we apply the same logic here with 5 parts for number 3, needs to overlap 1. Then we remove that one, and we have other 5 parts. Number 5 needs to overlap 6. And then 5 parts, there is only one choice left.
Number 5 must be contained in number 6.
Oh, yeah, actually, there is a good point. We almost always use superset. I think there is one case.
Number 5 is a subset. Line 67.
Line 67. Yeah, there is one case where it's a subset. So, yeah, there is a slightly variant there. But the principle is the same.
Yeah, and 2 is the last one.
And at that point, we have all the numbers because we had all our initial 4 certain guesses. And then we got other 3, another 3, and we got all the 10 digits. So
then
basically,
here we do magic with chaining.
Here we do a little bit of magic. Let me try to remember what we do. Oh, yeah. We have all the output values. We just need to build the number, the final number as a integer, as a U size. So what we do, we reverse. So basically, we read the output values
right to left,
from the right to the left.
Because they are numbers.
Mm-hmm.
So you read them from right to left.
Then we enumerate. So we also have an index. And the index will be, the rightmost will be 0, then 1, then 2, 3 for the
and
fourth
probably
digit.
Use it to do 10 at that power.
Yes, I think I could have used bit shifting here, maybe.
No, because we are base 10.
Oh, yeah, you're right.
We could use a reduce with a multiply, but it is different.
Yeah, this is probably the same thing, but
yeah.
Okay, and at this point we have the position and the value. So what we are doing is literally power of 10
by the value
for that position. Yeah,
and sum all together because they will go in.
And sum all together. There was another thing that I was doing to convert. S is the set.
You are taking the position from the set because you have an element and you are finding the position of that element in the array that is mappings.
Oh, yeah.
Mappings go from number to set, but you have to go from set to number.
Exactly, yeah.
So, or you invert the hash map and that is not an hash map because it's an array, or you create an hash map that goes from set to a number, and then you go by index on that hash map, or you go with the find position because I think it's linear position, but we have so few elements that we don't care.
Yeah, it will be 9 elements. So at this point, you just multiply. So here you will find...
They are at first 10 elements because
Exact. 0 to 9.
Yeah.
And then you multiply by the current position, basically, to the power. So basically, you reconstruct the number that way.
Yeah.
And at the end, you just do a sum.
Yeah, because one number will be in the order of 1, 10, 100, 1000, and so you put the figures together in a number.
And that's pretty much it. So we can run the test.
Everything together.
So I had here a test only for parse line. So this is basically should give us 5, 3, 5, 3. And yeah, one interesting thing is that you see this one and this one are the same.
Yeah.
Because it's 5 and 5, but then you also have 3 and 3, but the letters are not necessarily
they are
in the same order.
They're in different order, but we don't care because we use sets.
Exactly. But initially, this is something that put me a little bit off because I wasn't sure I was understanding the problem. Yeah, just this inconsistency that these two were exactly in the same order and this one.
And the other two were not. Nice.
And so this one is working, and if we run this one, should be working as well. Cool. So that's it.
So here, what can we optimize of all of this? Because there is a lot of exclusion, removing. The position down there in line 77 is a linear search, but on just 10 elements, who cares? I mean, also because I think that doing a hash map from set to number, aside that I don't know if you can in Rust.
I think you can.
Because the key of an hash map must be immutable, in theory.
Yeah, but we can build that at the end when we already have all the mappings, right?
Yes, we can do that at the end, doing a sort of the set and going to a string. And so you do a string to number type of a map. But doing all of this probably is slower than doing this position.
Yeah, probably. Also because we are doing it, 4 times?
But well, the position you're doing that 4 times per every line. So if we have 1,000 lines, you are doing that 4,000 times. I don't know how many lines are in the input.
I don't know either. We can check.
Typically
200.
200. Okay.
Yeah.
We are doing 2x4, 800 time a linear search on top of 10 elements. Is not that terrible. I mean, creating an hash map has the problem that then you're using only 4 elements of that hash map, but you have to create all 10 of them. So you increase you go in
the memory.
more constant time approach, but is more time, but constant. This approach can be faster or slower depending on what's in the right side, because if there is always 9, you are always scanning all the array. Instead, if it's always 1 0, you are always scanning only the first element. So it depends on the number that you have. So you have a more erratic time. And then here we can go in the field of Six Sigma. So it's better to be slower but consistent, or faster sometimes. Depends if you are doing microcontrollers or a web application.
Yeah. So I don't know. I'm pretty happy with this solution also because it runs fast enough. Like, yeah, I will probably just merge it as it is.
Yeah, I'm fine with that.
Cool. So should we do the next one?
Yeah, let's try to take a read at 9 and exercise
let me
9.
merge this one. For some reason, by the way, the Valgrind is failing, so probably there is something that needs to be fixed there.
Show me.
Let me get the last execution. Install Valgrind. Oh, it's failing to install Valgrind. That's interesting.
It's failing to install it. Okay.
It's failing to fetch something from Azure, so maybe there was some downtime. Let's rerun.
Or we are using Ubuntu latest, I think, for all of this. So
yeah, let's see if this one passes.
Let's see if it's Microsoft fault. Let's blame Microsoft. If I say Microsoft 3 times, Bill Gates pop up in front of me. No. Clippy pop up in front of me.
It's consistently failing. Look at this.
Okay, so I have to.
So maybe it was removed from the registry. How do we install this? Do we just do like an apt get?
I think so.
Yeah.
Sudo apt install Valgrind. Yeah, nothing more, nothing less.
Why does that?
Which version of Ubuntu are we using? You have to go in the repository, I think in the
view workflow file.
Yeah, exactly.
Oh, maybe because we're using latest, maybe it was removed from.
removed from latest. Oh, I don't like it, but
maybe now it's an optional package that needs to be installed.
I will take a look at it when I
Yeah,
have time.
probably we just need to set a version here or whatever. Cool.
Yeah, but
Well,
then
we can.
versions can be deprecated or going out of the Azure storage, and we are point blank.
Mhm.
But
Let's merge this anyway.
yes, it's not going to fail.
Perfect. Okay, so now we can look at the next one. Let's see if we can solve it fairly quick. We have like 15 minutes. So let's look at the README. I don't remember at all. What was this one? Okay, smoke basin. So what are we doing here? This
The
cave
caves.
seems.
Okay,
You read it. No, go.
No. These caves seems to be lava tubes. Part are even still volcanic active. Small hydrothermal vents release smoke into the caves that slowly settle like rain. If you can model how the smoke flow through the cave, you may be able to avoid it and be that much safer. The submarine generates an 8 map of the floor of the nearby cave for you, your puzzle input. Smokes flow to the lowest point of the area it is in, for example, considering the following 8 map. Each number corresponds to the 8 of a particular location, where 9 is the highest and 0 is the lowest location. Your first goal is to find the low points, the location that are lower than any of the adjacent location. Most locations have 4 adjacent location: up, down, left, and right. Location on the edge or corners. Oh my god, where are we? Scroll. Location on the edge or corners of the map have a 3 or 2 adjacent location, respectively. Diagonal location does not count as adjacent.
So basically, what I wanted to show here is that, for instance, 0 is the low point because 1 and 1 are higher. 1 is a low point because 2, 9, and 9 are higher. Then 5 is another low point because 8, 8, 6, and 6 are higher. And there is another 5 here because 6,
so on.
6, and 6.
So what do we have in the above example? There are 4 low points, all highlighted. There are 2 in the first. Okay, we saw them. The risk level of a low point is 1 plus it's 8. In above example, the risk level of the low points are 2, 1, 6, and 6. The second 6 is not highlighted. So fix your readme.
Yeah. We'll fix
the
it.
sum of the risk level of the low points in the 8 map, therefore, is 15. Find all the low points in your 8 map, sum all together, and what is your risk level?
Exactly. Cool. So let me do the git fetch all, git checkout. What's the name of this branch? Go back.
Year 2021. Yeah, that one.
Okay, and now git pull origin master rebase, and this will give us conflicts. Ooh, main.
You are so old school.
Why?
Because you are using master.
Okay, so accept both changes, and we just need to put a comma there, and that should be it. So git rebase, git add all, and git rebase continue. Okay.
And you also use Git, so you are old school.
What should I use?
I don't know. VS Code for everything, even the comments.
Oh, right, yeah. Cool. So let's fix that beautiful README first. Now let's look at the solution. So I suppose it's clear what we need to do. Of course,
we
the
have to
input
find
here is much bigger.
Yeah, obviously.
So we'll need to spend a little bit more time looking at all the low points. But essentially, we need to traverse this grid and look at the neighbors and decide which points are low points or not. Okay, now how did we solve this one? Let's see if we got fancy here. Maybe
There is a space with fixed but variable dimension. I mean,
so this one is using cost generics.
Yeah, exactly.
So it's creating an array of asides that you can specify as generic width and height. And then what do we do here?
That is a defer function that I have no idea what the fair trait does.
This is basically allows you to, so if you take a space, it will the reference to an array. So basically allows you to wrap it. So you wrap it as an object called space, which allows you to add extra methods, but you can still access to it as if it was an array. So it's a little bit of magic that, yeah.
Okay, so you still can treat the object like the type it was, but you can add the function on top of it instead of encapsulation.
So you are technically using encapsulation, but you can access all the attributes and properties.
But the object is not at one level inside you, is at the same level of you.
I think the trick is that Rust is smart enough to figure out when you use a method and you're using the ref to check if it's a method from the ref. But it's not really like inheritance. You're not really extending.
Yeah.
Okay, then we have a from string, which is for parsing.
Remember that inheritance is the devil.
Yeah, and it's not supported in Rust. There is no concept of classes and inheritance. Okay, so from string is basically used for parsing. So
yeah, is our parser.
We can check this in a second. Then what do we have? FindLowPoints, which is a method that is built in directly in space. So that's why it was convenient to have our own structure for representing space, because at that point we can have methods directly inside. So this will contain most of our business logic. And I think this is used for part 2. So let's ignore it. So part 1, what do we do? So we create a new space. We know that the input is 100 by 100. So we pass that as cost generics. And then we use the parse function that we can check above.
Here we don't have to turbofish the parse because we specified the type on the left.
On the left side, exactly. Yeah.
Okay, and we have to do that because we have to tell him to tell to the compiler the dimensions, the sizes. Okay.
Yeah. And we need to do that because we are not using vectors, which are heap allocated, but we are using arrays which are in the stack. So you need to specify the dimension up front. And cost generics are a way to keep that a little bit generic so that you can have different implementation using different sizes.
You can declare variable of the same type with different dimensions if you need it.
Exactly, but this size needs to be known at compile time, so it will be applied at compile time. Okay, then at that point we use our function FindLowPoints that we need to check to get the low points, and then at the end what we wanted to do was
low points. What is giving you back a vector of 2 coordinates.
So x and y of that low point.
Okay, so it's not giving you back the value of the low point, but it's giving you back the coordinates of the low point. Then we have to map the coordinates to the value itself.
Exactly. And I don't remember why we do +1 here.
Because it's written in the README to add 1.
Oh, okay. I
The
missed
risk
that.
level is the value of the low point plus 1 is written in the README. Don't know,
Okay.
ask them.
Then we return that and we sum. So that should be, the logic in itself should be pretty simple. What
And we can do what we do in line 133, so using space as an array, because there is that the ref that the trait the
exactly.
ref if we didn't add that trait
We should have
implemented,
done something like
we
this.
should have done dot zero dot dot zero. Okay, that one. Okay, that
Which
is
maybe
ugly.
works. I think it will work anyway. Yeah, works.
Yeah, but it's ugly to see, to be honest.
Yeah, pretty much.
Like this is bad.
Or we should have used a name, like call it, I don't know, space.grid, and then you have to do .grid and stuff like that.
Yeah.
Okay, so
like
let's
we did in a lot of other exercise, to be honest.
Mm-hmm.
So
yeah, I think here I wanted to be fancy and try this deref thing. It was a good excuse.
Nice.
Okay, so let's look at this from string, which will be fairly simple because we will have lines. Every line is a set of numbers, so every character is a number, and then we just need to take all the lines and parse every single character as a number. So here is interesting because, again, we are in the context of generic implementation block. So W and H will be width and height that will be known at compile time, but we can use them as constants in our code. So we create this data that initially is going to have all 0 values, and it's a grid width by height. Then what we do for every row, what we do is for every lines we enumerate. So we have row ID, and the line. And then for every column, we do the same. And we get every single char, we map it to this C2 digit 10. Is basically a way to say, take that character and interpret it as a digit in radix 10. We convert it to a U8, and then we enumerate. So again, we have row ID, column ID, and the value.
And the value as a U8.
And what we do is basically say, in this row ID, in this column ID, set this value. So initially everything is 0, and as we go through the numbers, we fill all the positions in our grid. And then at the end, we return an OK space data. OK because we are using from string, and from string can fail, even though we are not really handling failure here. We are assuming that the error type is a unit type because we never fail, but we still need to use an OK. Then we wrap everything in space, and space just needs to receive the grid.
We never fail, we just panic.
We will panic if the input is not valid, because this will fail, or I suppose if the length is not really the one we pass here, we might go out of bound.
Yeah, we can go out of bound, and
all right,
stuff will happen.
So the other interesting function is, once we have a grid, how do we find the low points? And here what we want to do is return a vector of coordinates, where coordinates are just tuples with x and y coordinates in our grid. So initially is an empty vector.
And then mutable empty vector, yeah.
What we do is basically, again, we traverse the entire grid. So for every row and for every column, we will have a cell, which is going to be already a U8. And what we want to do is basically look at the 4 neighbors. So if the 4 neighbors, of course, for every neighbor, we need to check if they exist. So if we are in the first row, we know that there is no top to look for. So we need to check, are we a list in row number 1 to make sure that there is something above. And if there is, we push. We keep here a vector of all the neighbors, which is going to be maximum 4. So we can already pre-allocate it with capacity 4. This is a little optimization trick to avoid that the vector gets...
still putting it in the heap, even if we do with capacity?
It's still in the heap, but it will not... I mean, it will be already of that size. I'm not really sure what's the default, but if this was a bigger number, chances are that initially the vector will be maybe size 2. Then
Yeah,
you
I
consider
think there is a reasonable amount of space that is allocated when you declare an empty vector. I mean, it's not going to be 0. It's going to be something bigger than 4.
Maybe, but let's say that is 2. Here we are already
Yeah, we
pre-allocating
know.
4.
We let know the compiler to go higher.
Exactly. So what we do, we push all the neighbors, making sure that we don't look out of bound. Then
Yeah.
at the end, once we have all the neighbors, this is going to be a low point only if this all statement is valid. So if for every neighbor this n, so the cell is lower than n, where n is the value of the current neighbor. So if that statement is valid for every single neighbor, then we push the low point into the set of low points. So we push the coordinates.
At the end, we return it. Yeah.
So that's pretty simple. It's just the only complexity is to make sure that you are looking inbound. It's also interesting that with these constants, you can do expressions, again, because these values will be known at compile time. But by the way, just for the sake of curiosity, you cannot do expressions, for instance, here, if we wanted to do w minus 1, here you cannot do that expression. I think this is a limitation of Rust, and it will be eventually fixed.
So you can use the stuff in that constant in expression, but not if you are specifying another type with that.
I think you cannot use it as a size of an array. You cannot put an
Just as a
expression
size of array.
Yeah, I think that's the limitation. But there is, I saw some time ago that there is something in the backlog that eventually will be addressed. So it's just a missing feature in the compiler, as far as I understand.
Okay.
But here you can do it. So in if statements, you can have W, and this will be essentially replaced at compile time as a constant.
Yeah, with 99 in our case. Yeah.
Okay, so that's pretty much it. I think we can run part 1, right?
Yeah.
And let's see if this works. It does. Cool. Okay, do we have time to go through part 2? I think it should be fairly simple, so maybe
Let's
can
read
finish.
it.
Right, so part 2, actually, let's go to GitHub because it might be a little bit more readable. README. Okay, so part 2, now we need to find the largest basin, so you know what areas are most important to avoid. A basin is all locations that eventually flow downward to a single low point. Therefore, every low point has a basin, although some basins are very small. Location of 8, 9 do not count as being in any basin. And all other locations will always be part of exactly one basin. The size of a basin is the number of locations within the basin, including the low point. The example above has 4 basins. So here there should be, I don't know if it's very readable, but characters should be in italic to tell the basin. So for instance, here 3, 2, and 1 constitute a basin. All the 9s are always ignored. And this is size 3 because there are 3 items in this basin.
Okay. Then if you scroll.
So the top right, yeah, this is size 9 because you have 0, 1, 2, 3, 4, 0, 1, 2, 1, 2, and 9 stops the basin there. So here you have 1, 2, 3, 4, 5, 6, 7, 8. How is that 9? Size 9.
1, 2, 3,
1,
4,
2,
5,
3.
6, 7. 9 because there is the 4 on the line below.
Oh yeah, okay. here, this one as well.
Because it's not square. Can have any kind of shape.
Yeah, exactly. It's only, so it's like a flood fill. It's only the 9 that is like an hard border. Okay, so this one goes here, then here, then here, here. Wait, here. Okay, makes sense. So the middle basin sides 14, and this one, yeah, this one is a little bit more complicated because all these 9s are a border. This one is a border. Then you have this 3. This is a border, then border, all of this stuff, a border, and then all of this, another border, and then 8 is the only one, and these are borders. And so on and so forth. So yeah, if these were pixels, you can imagine that all the 9s are black pixels, and you are trying to see how big are the regions separated by these black pixels. Does that make sense?
Yeah.
And basically what we need to do is to find the 3 largest basins and multiply their sizes together. In the above example, these are 9, 14, and another 9. So you multiply those 3 values, and this is the answer. In our case, the number will be much bigger.
Obviously.
Righty. So back to the code. So part 2, I'm just going to read this, and then most of the logic will be in this basin sides function. So we redo the parsing, we get our space. Then here we are using a binary heap, which I don't even remember what is it. So it's a priority queue implemented with a binary heap. Okay, so allows us to extract
because
the
we
top
want
3 basins.
The top 3. So while we go through, we keep the top 3 instead of sorting and taking the first 3 elements.
Yeah, so this is just an optimization, but it could have been a vector, and then we just find
it could have been a vector, sort it, and take the first 3. We
Exactly.
don't have 1 gazillion of them. The binary heap is just the advantage that while you go through and you add stuff, they are already sorted.
And you can easily say top X, basically. All right, so then and it's a U sides because we only care about the sides of the basin. So we only need to keep the sizes around. We don't really need to keep coordinates or stuff like that. Then what we do is we find the low points because these are generally the starting points of a basin.
They are the starting point of our fluid field.
And then what we do, we iterate over the low points, and we map basically the basin size, take a position, which is the position of a low point. And at that point, we collect into a binary heap. Then with that, we can just do top 1, top 2, and top 3 by popping from the heap, and we just multiply those 3 values. Make sense?
Yeah.
Okay, so now we just need to look at these basin sides, which we start from a low point, and we need to be able to count. Basically, we do a flood fill from that point and count how many pixels or cells we are covering. And I just noticed we had a comment of somebody saying hello, and I totally ignored it, so apologies for that. Anyway, back to the code. So what we are doing is that we need to keep track of the pixels that we already visited, and basically we keep walking until either we visited everything and there is nowhere else to go, or when we find a boundary, then of course we cannot keep exploring in that direction. In our case, the boundary is a 9, so we'll stop if we hit a 9 in that particular direction. But for every point, we always need to explore all the neighbors.
So visit is an empty vector.
So visited initially is an empty hash set that will contains coordinates, and then to visit is the neighbors that we find that we might need to explore.
The cell that we have to visit.
Exactly. So what we do is, of course, we start with
from the first one.
From the first one. Actually, here I think I could just use a regular vector.
I think the vectq, because we are always popping from the front, is faster.
It could
because
be, yeah.
A standard vector you can work in any position. A vectq you can only work on the start or the stop or the end, and so it has a faster operation to do so.
Yeah, it's probably implemented as a circular.
I have
list.
no idea how it's implemented, but it's faster, because if you use a normal vector and you pop from the front, probably there is a shift of all the data, and that can be crazy expensive, CPU wise.
So what we do is, while there is stuff to visit, basically, we take the current element by popping from the front of the to visit vector queue, and we insert that in the list in the set of visited pixels.
Cells, yeah.
Then what we do, we take the current cell value, because we need to check if that value is 9, for instance. And then we take all the neighbors. So the top one, the right one, the bottom one, and the left neighbor. We don't look at diagonals.
Yeah.
And what we do, we check for everyone if it has been already visited, if exists. So if there is a position, if there is a cell in that position and it has not been visited already, it's pushed in the visit list, to visit list. And we do that for top, bottom, left, and right. And then at the end, what we do, we just count how many pixels we visited.
I don't get why you check the current cell value.
Because that value cannot be 9.
How can it be 9? Because we start with empty, with a low point, so it can't be 9 because it's a low point. And we add it to the vectq only if it's not 9. How can you have a 9 in the vectq if you are never putting a 9 in the vecq?
So you mean we could remove this one?
Try to comment and run the test.
Or is it an optimization? I think it might be an optimization, because this is basically saying if this is an 8, don't even bother looking at the neighbors, because the neighbors can only be 9.
Yes, this can be an optimization. It's true.
I think that was the idea. But you are right, like it's not needed. It would work anyway. It will just push more and do more loops.
Yeah. But you're right. If it's 8, don't go on. Count it, but don't go on.
And it will be counted because it's already inserted in the list of visited points.
Okay. It's not needed, but can give some more speed.
So that should be it, and we can run the test. Part 2 works. Cool. What else can we do here?
I mean, that optimization, we can benchmark if it's really an optimization or not, but I don't think it will change a lot. It's just one additional check in if.
And that will save you from every time that there is an 8, you are saving 8 push, and the Q and Q at the Q from
that
4 times,
queue.
Potentially 4 times, up to 4 times. Yeah.
It is theoretically with a vector Q is faster than with a vector, but in any case, it's better to avoid you use this stuff.
Alrighty. So do we stop here for today?
Yeah, let's wrap it up. You can find the recording on YouTube. The link is on the Twitch in the About section. It's on Twitch on the About section. If you are watching this on YouTube, we do live streaming on Twitch every Monday, 5 p.m. UTC. Make sure to check the Twitch link in the YouTube description. Give us a follow and everything else. Feel free to leave comment and open PR. The repository of this code is at the banner. Yeah, there. Everything is well accepted. We're trying to learn Rust. Don't expect our solution to be the cleanest one or the more idiomatic one, even if they are getting way better than when we started. If you know better ways of doing stuff, let us know so we can learn. Thank you for the participation. Thank you for the comments and so on. Are we going to rate somebody or not?
Yes, I'm triggering the raid. So we'll see you at the next one.
Thank
Thank
you.
you. Bye bye.
Bye.